Today, we're going to continue looking at double integrals. Remember that the thinking behind double integrals is the same as the thinking that we had in single variable calculus. We've just upgraded finding the area under a curve and above an interval to finding the volume below a surface and above a region, where an interval is very easy to describe. Start at A, end at B. A region in the XY plane can have any kind of funky shape that it wants. And so our job is going to be to describe that funky shape in a way that the integral can understand. Yesterday, we also talked about the basic idea. We're going to figure out what X is between and what Y is between. We got to make sure that of one of those has to be constants. Then the other one can be variable. In a double integral, the last integral, the outside integral, that has to only involve constants. The previous integrals can involve functions of the upcoming variable. So we're going to continue with the exercise we were doing yesterday. We're going to set up a region, and then we're going to describe it with a dx dy integral, and then also a dy dx integral for practice. Remember that we're not evaluating the integrals. We're just setting up the double integral so that we can calculate. But that comes later on a machine. Even if we're going to use a machine to set up our integrals, we have to tell the machine what integrals to find. So that's why we need to be able to describe them properly. Right, buddy? Is that in the way? Okay. Good dog. Good boy. All right. So let's take a look at our example, our first example. I've got the region bounded by y equals x squared, y equals 9, and the y-axis. So yesterday we had the x and y-axis as boundaries. Here, I'm using y equals x squared, the function, the horizontal line y equals 9, and the y-axis. We're going to set this up. We're going to describe this with two different double integrals. One of them will be a dx dy, and the other one will be a dy dx. So we're going to set up one of them is going to be a dx dy integral. So if I put a dx first, that means this first integral is going to be what x is between. And then with dy second, the outer integral is going to be what y is between. The last integral, or the outside integral, has to be between constants. So we just look for the lowest value of y. We don't worry about anything being curvy. We just look for the lowest value of y and the highest value of y. Y goes between 0 and 9. That when we start off with constant values of y. Now we have to look at what x goes between. And so what we're going to do is pick a generic value of y and find the lowest value of x and take that up to the highest value of x. So the lowest value of x appears to be 0. And the highest value of x appears to be at the function. So x starts off at 0 and ends at the function, but the function says y is equal to x squared. We need to know what x is equal to. So if y is equal to x squared, then x is equal to the square root of 9, a square root of y. So if y is x squared, then x equals the square root of y. So there's a double integral. That's how we would set up the inputs if this is the region R over which we are trying to integrate. We also need to do things the other direction. I need to be able to set up a dy dx integral. In this case, it wouldn't matter that much. They're pretty much the same. But to favor one, excluding the other means that you don't want to know something. You want to exclude something from being known, and that's ridiculous. That's like the opposite of what we want to be doing. So here my y is going to go first, and if I set up a dy dx integral, then the x goes last. The last integral has to be constants, and the lowest value of x is 0, and the highest value of x is 3. So always just have to go with the lowest and highest values of x. That's what x is between. The two constants, 0 and 3. We're going to get the shape from the y. So for what y is between, we'll pick a generic value of x, pick some x between 0 and 3, find the lowest y, and follow it up to the highest y. It's a little bit different than the one that we saw yesterday, where the highest y is 9. Oops. Y stops at 9, and y doesn't start until the function. So here is where the function starts, and that's where y is equal to x squared. So y goes from x squared to 9, and x is between 0 and 3. The way we evaluate these integrals, I know we haven't talked about evaluating them, but the way we evaluate them is going to be from the inside out. The first integral we evaluate is the dy. After we take care of that, we can integrate dx. But the way we construct the integral is to go from the outside in. Start with the constant bounds and then describe the funky bits. Any questions? All right. Let's do another version. I'm still going to cut this out of the 3 and 9. So let's cut this down a little bit more and see what happens. So I'm going to keep the y equals x squared. I'm going to exaggerate it a little bit. But now instead of using the y-axis and the line y equals 9, I'm just going to draw a line. I'll make the line alternate color. From 0, 0 to 3, 9. Just going to make some riveting YouTube later. All right. Heard a story. I don't know if it's true, but I heard a story that when Scorsese, right, was making Gangs of New York, George Lucas came to visit and said, "Hey, you know, you can do all this with computers," because they had like elaborate sets built and everything like that. And I think of that every time I sit here and have to erase something on paper, on camera, because I don't edit my videos. I imagine George Lucas showing up at my house and you know, you could do that on a computer. It would look better. It would be more precise. And then all the filmmakers would be like, "Oh, and you could edit your videos." I'm like, "Oh no." So what do we got here? I still want to keep this parabola y equals x squared. But I want, instead of using this big corner here, I want to cut it off with the line y equals 3x. And that's the region that we want to get. So here's the region that we want. We're going to do the same thing. We're going to set up a dx dy integral and a dy dx integral. Let's go the other direction this way. Let's start with the dy dx integral. So I'm going to have two integrals. My function right now doesn't matter. And I want to set up a dy dx integral. So my first integral will be what's y between, and my second integral will be what x is between. In the second integral, that always has to be between constants, and x is between 0 and 3, just like before. We're going to get the curvy parts by figuring out what y is between. So I'm going to pick a generic x value. We pick a generic x value and figure out the lowest y value and send that up to the highest y value. In this case, the lowest y value is going to be from the parabola, x squared. And the highest y value is going to be from the line, 3x. So what we're saying is, for the values of x between 0 and 3, y is between x squared and 3x. So if we had to describe this region to a double integral, we would say, for the values of x between 0 and 3, y goes from x squared to 3x. That's why that last one has to be constant, because the first one is going to be in terms of x. So when we just say y is between x squared and 3x, that's not specific enough. We have to say what x values we're using, and that's the last integral. So let's set this up as a dx dy integral. In a dx dy integral, the y's are between constant values. We're going to say, what y values are we worried about? And we're still worried about y between 0 and 9, so we keep those constants. The last one has to be constants. The earlier integral can be a function of upcoming variables. So let's pick a generic y value. Pick a generic y value and find the lowest x and the highest x. the lowest x starts at the line. The lowest x is starting at the line, y equals 3x, but I need the x value in terms of the y, because I'm starting with a y and figuring out what x values I need. So if y is equal to 3x, then x is equal to y over 3. So we'll start at y over 3, and we'll end at the parabola x squared, y equals x squared. So I'll have to rewrite that to be the square root of y. So for the y values between 0 and 9, we take the x between y over 3 and the square root of y. What's x between? What's y between? Any questions? How's everybody okay? This fancy circle making thing, and then I just draw the lines freehand. I don't know. I know, George, I could do this all on computers. All right. Let's suppose that our region, let's see, this is going to be at 3, 0. And this will be at negative 3, 0. And this will be at 0, 3. So let's suppose that this is the function y equals square root of 9 minus x squared. And we want to describe this region with a double integral in both directions, even though one direction is going to be kind of inconvenient for us. Right. Let's do a dy dx integral first, because x goes from 0 up to a function. Anytime x goes from a 0 to a function, if one variable is a function of the other variable, if you can identify one as an independent variable, that should be your outer one. So let's describe this. Oh, sorry, your dependent variable should be the outer one. Your independent variable should be the outer one. There's two ways to say that sentence, and I'm clearly mixing them up. Let's do a dy dx integral. Let me just start with that. So I'm going to write my y between, what's y between, and I got to figure out what x is between. All right, so I've got this semicircular region, and I've decided to set up a dy dx integral. So I'm going to figure out what x is between, and that's got to be just the constants. So the lowest x value is -3, and the highest x value is +3. So x should go from -3 to 3. We get the curvy part with the bound on y. So now we're going to pick a generic x value and figure out what y is between. So I'm going to pick a generic x value and find the lowest x value, the y value, and the highest y value. The lowest y value is down here on the x-axis where y is equal to 0. And the highest x value, the highest y value at this generic x value is at the circle. So we'll stop at the square root of 9 minus x squared. There's a double integral describing this semicircular region. Because this is math class, we have to learn things backwards and forwards. Now we're going to set up a dx dy integral. So we're going to integrate. We'll make two integrals. So now we're going to set up a dx dy integral. Always start with the outer integral first, even though when you're evaluating, start with inner integral first. The outer integral has to be between constants, so we need the lowest y value and the highest y value, regardless whatever curvy stuff is going on. The lowest y value is here on the x-axis, where y is equal to 0, and y stops at 3. So we're going to integrate on y from 0 to 3. We're saying for all the y values between 0 and 3, x is between, and then we have to figure that out. Now we're going to pick a generic y value, and find the lowest x and the highest x. In this case, y is equal to the square root of 9 minus x squared. So this comes from the circle. There it is. This comes from the circle x squared plus y squared is equal to 9. In this case, we only have positive y values. That's why when we solve this equation for y, we just care about the positive y values, because we're first and second quadrants. But now here we need some negative x values and some positive x values. So if we solve this for x, we'll not just have the square root of 9 minus y squared. So the square root of 9 minus y squared will be the semicircle in the first and fourth quadrants. But I need the semicircle in the second quadrant as well. So I have some positive and some negative x values. The lowest x value is the negative x on this circle. So it starts off at the negative square roots of 9 minus y squared and goes to the positive square roots of 9 minus y squared. So we had to know some stuff about circles. If x squared plus y squared equals 9, then y equals plus or minus the square root of 9 minus x squared. The plus is the top half, the minus is the bottom half. But we could also write x as a function of y. X is plus or minus the square root of 9 minus y squared. Plus is the right half, minus is the left half. So the left half of the circle is minus square root of 9 minus y squared. The right half of the circle is plus the square root of 9 minus y squared. We're not worried in this case that we have the bottom half of the right half, because we've already restricted that by saying y is only going from 0 to 3. So these are the two halves of the circle, plus or minus square root of 9 minus y squared. Any questions? How's everybody okay? If you're a little bit confused by what's going on, that's okay. That is the correct reaction. It's day 2 of describing regions in this weird, funky way. I don't need it to be clear. I just want it to be a little more clear than it was yesterday. That's the goal. Better than yesterday. Not going for good, we're going for better than yesterday. Which really, it's all we can ever hope for. If at a certain point we think everything is perfect, we're probably just not looking hard enough. Any questions? All right, let's do one more. It's going to be a variation of this circle. I'm just going to rotate this 90 degrees so we can really get at this plus and minus business. Plus another, I get to use my cool circle thing one more time. So this is still going to be x squared plus y squared equals 9. Let's describe this with a double integral. Let's describe this with 2 double integrals. So we're going to have the same thing. When x squared plus y squared equals 9, I can write y, this is y as a function of x, or 2 function of x. It's plus or minus the square root of 9 minus x squared. This represents the top half and the bottom half. I can also write x is plus or minus the square root of 9 minus y squared for the left and the right. So if I wanted to, I can describe this as a function. I can say x is minus the square root of 9 minus y squared. And that's the left half. But notice that as far as y is concerned, I need the top and the bottom. So I need the plus and the minus. So let's set up our two double integrals, a dx dy and a dy dx. So let's start with a dx dy. And end with a dy dx. Sorry. Start with a dx dy. So once again, easiest to start setting up the outer integral first because it just needs to be between two constant values. The lowest y value of this region is -3, and the largest y value of this region is +3. So the y's go from -3 to 3. Now I need to pick a generic value of y and see what x values it's between. So I'm going to pick a generic value of y and just find the lowest x and the highest x. The lowest x is on the circle, and for all these values of y, I can just say x is negative square root of 9 minus y squared. It's always the left part of the circle. So the lowest value of x is on the circle, negative square root of 9 minus y squared. And the largest value of x is 0. So for the values of y between -3 and 3, choose the values of x between negative square root of 9 minus y squared and 0. I didn't have to exploit the plus or minus business because for this left half of the circle, x is a function of y. Now we're going to need some plus and minus stuff for my dy dx integral. Not mine, our. Not our, everybody's. Until Disney comes along and buys it. Or a bunch of venture capitalists come and buy my catalog of calculus videos. I think they own all the music now. They just need to expand. So now we're going to set up a dy dx integral. I need to find the lowest and highest values of x, just two vertical lines that will encompass my region. The lowest value of x is down here at -3. And the largest value of x in the whole region is what here at x equals 0. So for the values of x between -3 and 3, now what we're going to do is pick a generic x value and find the lowest and highest y values. So I'll pick a generic x value and find the highest and the lowest y values. So now we're using the top and the bottom half of the circle. So for the values of x between -3 and 0, choose the bottom half of the circle, negative the square roots of 9 minus x squared, and the top half of the circle, positive the square roots of 9 minus x squared. For any x value, go from the bottom half of the circle to the top half of the circle. We don't have to worry about what's going on in the right side of the circle because I've restricted that with the x values. X only goes between -3 and 0, so I'm not worried about this. I'm not going to get anything on the circle over here. And that's how we can describe this region with a pair of double integrals. Any questions? I forgot you have to color it in afterwards because the highlighter pen takes too long to dry. You're all looking at me very suspiciously like there's some kind of trick, and there's no trick. It really is just that easy. Or maybe you're looking at me and you're all concerned that I'm wrapping this up and it seems so confusing. Remember, we've only done like 6 examples total. So if you're still confused about what's going on, that is correct. You need to start just doing some problems. I think the best problems to start with are the ones that we've already done. So you don't watch someone play a song, say, and learn some other song. Start with the song that you're familiar with. You know what it sounds like. You know what I mean? So start with these examples. Go through again. What's x between? What's y between? Think about the big ideas. We're setting up a double integral. The last integral has to be between constants. That's the easiest thing to grab. Pick a generic value of that variable and figure out what the other variable is between. The last integral has to be between constants. The previous integral can use functions of the upcoming variable. Any questions? Comments? Snide remarks? All right. There are some homework assignments from chapter 16 that have been posted. I think they were originally due on October 3rd. I hadn't even talked about them yet. And so I have moved those to October 10th. So work on those, practice some other double integrals. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.